Well, thank you very much for inviting me, and congratulations on your new center. It seems like in the last year there's been a lot of activity around Europe and around the world on creating these centers, so I'm expecting great things to happen soon. So today I thought I'd tell you about our experience in trying to commercialize quantum technology and bring it along to a point at which people who aren't expert in quantum mechanics can actually use a machine to do computing. So I'm going to talk to you a little bit about D-Wave, who we are, where we come from. I'm going to talk about our particular approach to quantum computing, which is not, I would say, mainstream at this point, but it has certain advantages, we think. I'm going to tell you about the product that we have currently, which is currently a 512 qubit quantum computer, and some of the applications that we've run on it, just to give you a sense of the flavor of what they are and how you might program it. And then I'm going to say a little bit about the burning questions which is on everyone's mind at the moment. Is it really quantum? And is it faster than what you can do classical? And the exciting news is we're just about to release a brand new processor, and I'll tell you a little bit about that and how it's different from the one that we have commercially available today. And then maybe I can end with sharing some lessons learned from D-Wave's experience and pass along some thoughts for what might be beneficial to your Center for Quantum Engineering. So D-Wave was founded quite a long time ago for a startup company back in 1999. Most startup companies don't go this long on investor funding. We've been very lucky to have some very, very patient and good investors. We started off, first of all, exploring the possible schemes for making a quantum computer. And around 2004, we did a down selection to pick what was called the adiabatic quantum computing model, because that looked like the shortest path to a near-term realizable quantum computer. And since that time, we've been manufacturing those devices, and they started selling them about 2011. Our business model is to sell the actual quantum computing hardware, as well as selling software services to write applications for other people to use that hardware. And eventually, we want to move people to essentially a quantum cloud computing model, where you don't actually have to have one of our machines in your building, actually use a D-Wave machine in Vancouver remotely over the cloud. For a small company, we currently have about 120 people. We have very large patent portfolio, over 100, I think it's over 110 issued patents at this point. 70% of the world's patents in superconducting quantum computing of all kinds are D-Waves. Although we have a bit of a reputation for being secretive in some quarters, we're actually not. The opposite is the case. We've published over 70 peer-reviewed papers, which is exceptional for a startup company. You don't hear other companies in Silicon Valley producing papers in those kinds of quantities. And for a tiny company, we have done big things with our patent portfolio. We were actually ranked as the 4th most important company in terms of computer systems engineering by IEEE in 2012 or 13. So far, we've raised about $150, $160 million, and we that's a combination of venture funding and government grants. And recently, we've been supplementing that with revenues from system sales. So we were very lucky to have several top-tier investors. Draper Fisher Jurvetson is one of Silicon Valley's top firms. Goldman Sachs, Harris & Harris is a nanotech fund. And Jeff Bezos, the founder of Amazon, is also an investor in D-Wave. Steve Jurvetson, the J in DFJ, he's actually on the board of 3 companies, D-Wave, Tesla, and SpaceX. So he really likes the outlandish, the big play companies. We're involved in only a handful of vertical markets, I'd say, but they're big markets, the defense sector and intelligence. In the defense area, we have a relationship with Lockheed Martin. We sold the system to them back in, I think, 2012 was the first one. IQT is a venture capital fund that looks for early stage technology and funds it into the US intelligence agencies. Google and NASA you've probably heard of. We have a machine deployed at NASA Ames under funding from Google. It's called the Quantum AI Lab, and they're doing good things with that. And we also have an ever-growing repertoire of universities with whom we work. For example, USC in America, UCL in London, and others around the world. And I hope this year to announce a couple of new players in the finance and the energy space as well. So what is quantum computing? Well, to us, it's actually very simple. We conceive quantum computers as being machines that harness physical phenomena not available to a conventional classical computer. In particular, the important phenomena are superposition, the idea that if a bit can be a 0 or a 1 in a classical computer, in a quantum computer it be a combination of 0 and 1 at the same time to different degrees. That's called superposition. Another phenomenon we use in our system is entanglement. This is the idea that if you have a quantum memory register on n qubits and you perform an operation on one subset of those qubits, if the qubits are entangled, then even though you don't touch them, you can actually have a side effect on qubits simply by performing an operation on the complementary set of qubits. It's a very counterintuitive idea because that does not happen at all in any classical computer. And finally, the effect that we make use the most of is quantum tunneling. This is the idea that if you can specify your problem in terms of essentially an energy landscape, then there's a physical mechanism quantum mechanics provides that lets you explore that landscape in a new way. In particular, you can tunnel through those energy barriers to go from one local minimum to another local minimum without having to go over the top. And our machine has all of these phenomena at work going on in it, and it uses them all to some degree in computation. Okay. So our approach to quantum computing, first of all, is inspired by picking a theoretical model on which to base our computer. And it's always amazed me that there seems to be no end of choices available to choose the theoretical basis for your quantum computer. So most of the world is following the gate model approach, just by creating quantum analogs of the classical logic gates and Boolean circuits. Even big companies like IBM and BBN are pursuing that kind of approach. The one-way quantum computer is the idea that if you create a reservoir of entangled states as a starting point, then you thereafter only have to do one qubit operations or measurements on the entangled states to do universal quantum computing. And as Charlie was saying before, topological quantum computers have a lot of promise because of the inherent resilience to noise caused by topological braiding operations. And Microsoft is investing in bringing that technology along. And finally, the adiabatic approach to quantum computing, conceived of really by Ed Farhi in America and Nishimori in Japan, is the approach that we picked because we thought that was the nearest term to getting a computing device of significant scale. Now, the good news is that it doesn't actually matter which of these models you pick because there are polynomial equivalences provable between all these models. So anything you can do, any quantum computation you can do in one of these models, you can in principle do in one of the other ones. Of course, in practice, it does make a difference because some of the models are actually easier to implement in hardware than others. So our choice was basically inspired by the adiabatic quantum computing model. So what that is an approach to computing in which the idea is to start the system off in a low energy state that's easy to get into. Typically, it's an equal superposition state, which all solutions are equally likely. And you achieve that state by applying a very large transverse field. So you put all qubits in an equal weighted superposition. Then you slowly turn off that transverse field as you turn on a field that expresses your problem that you want to solve. So you turn off the A coefficient in the Hamiltonian as you turn on the B coefficient. So by the end of the annealing process, as time goes along here, your coefficient is entirely B and the A has gone to 0. And the idea is, if you can make this final Hamiltonian be one that encodes your problem, and you start off in the ground state of the initial Hamiltonian, then there's an old theorem of quantum mechanics called the adiabatic theorem that guarantees that you stay in the ground state of all the instantaneous Hamiltonians pass through. So if you start off in the ground state of the easy to get into Hamiltonian, with the equally weighted superposition state, and you turn A off as you turn B on, and the final Hamiltonian is such that the lowest energy state is the optimal solution to your problem, then the adiabatic theorem says you should be carried to your global optimal solution, ideally. That's basically the idea. Now, what's the time that's supposed to take? Well, the theorem says that the time it takes to go from the initial state to the final state needs to scale as the inverse square of the minimum gap between the ground state and the first excited state if you want to guarantee that you end up in the global optimal ground state of the final Hamiltonian. That's the theory. So we started making devices that implement this approach to quantum computing. And of course, once you've got a device, you can start playing with it in ways that the theorists didn't imagine. And we did exactly that. And we found that empirically, first of all, we were actually getting higher problem-solving success probabilities if instead of running the computation once very, very slowly, we ran it several times very, very quickly, and then took the bit string solution that most minimized our objective function as the best relative answer found. Now, since we did that purely empirically, recently a paper by Ed Farhi and Peter Shaw in America and by Nishimori in Japan has proved that quantum annealing with these fast repeated operations gives you exactly the same performance as adiabatic computing, annealing slowly once. So now there's a theoretical justification for what we actually discovered accidentally, experimentally. The other thing is we don't assume that the computer is operating at zero temperature, which the adiabatic theorem does. And the reason is, you can't actually make any piece of real physical hardware that does operate at zero temperature. Can't do that. We make our machine very, very cold. The current machine runs at 20 millikelvin, but that's still not zero. And so there are still some thermal effects operating in the computer. Now, the good news is that from a computer perspective, thermal annealing and quantum annealing are both beneficial. So there are some computations that actually do very well using thermal annealing effects and some that do well using quantum annealing effects. So it's not detrimental at all to have both annealing processes going on in the hardware. Finally, we just determined very early on that you could make a universal adiabatic quantum computer. In fact, we made a prototype chip like that several years ago. But we could make a much simpler Hamiltonian a lot more easily at scale. And if you look at the space of problems that this non-universal Hamiltonian addresses, it's almost all of the available market for the machine. So we didn't think it was worth the additional risk of taking on the job of making a universal Hamiltonian when a simpler non-universal one would address most of the commercial market. So that's what we made. If in the future we change our minds, we now have designs for a complete universal quantum adiabatic machine as well. But right now we're making the non-universal version because it's easier and it gets us most of the market. So there are many reasons why we did this. It was easier to implement experimentally, and the adiabatic model, the annealing model in particular, is naturally well suited to solving these large optimization problems. And these are of high commercial value, so that's why it's worth doing. So how it works sort of conceptually is the problem that you want to solve is presented to the machine in terms of a set of biases and couplings in an Ising spin model, which essentially designs an energy landscape. So you're essentially taking your original computational problem you want to solve, and you're re-expressing it in terms of an energy landscape. Now, what's interesting about our machine is that all computers in human history before ours, every single one, whatever it was, could only search these energy landscapes using an algorithm that explored the surface of the landscape. Our machine is the first in human history that has the additional capability of tunneling through the landscapes. It's a new physical mechanism which we've harnessed to the service of computation. And that's a quantum physical effect called quantum tunneling. So the product that we've made, which is our current product, is the D-Wave 2. It comes to the customer inside a large box with a set of 19-inch racks on the side. So this large box is actually a very important part of the device. It's a shielded room. It cuts out all the radio frequency interference from the outside. So if you're in that room with the door closed, your cell phone doesn't work. Then we also have to null out the magnetic field on the chip, and we have to null that field out to a very exquisitely fine detail. So if we put a D-Wave machine here in Finland, we put a D-Wave machine in California, we'd have to do a local calibration of the chip to null out your local magnetic field to less than 1 nanotesla in each of 3 dimensions. That makes it 50,000 times weaker than the Earth's magnetic field. It's one of the most magnetically quiet places in the universe. Not only is it magnetically quiet and radio frequency quiet, we also have to cool the chip down to 20 millikelvin. That's 150 times colder than interstellar space. So it's really, really cold. So if you were to look inside the box and take the skin off the dilution refrigerator, you would see this cryostat, and the job of the cryostat is to step the electronics down from room temperature all the way down to 20 millikelvin temperature. And everything connected to this bottom plate, which is about 10 kilograms of metal, goes to 20 millikelvin. Now, interestingly, we have Finland inside. So we actually, in some of our systems, we use a Finnish dilution refrigerator from Blue Force here. And I know our team in Burnaby is really impressed with the technology that Blue Force is providing. So we're very happy to be using Finnish technology. It's great. So this is what the processor looks like today. This is the actual quantum chip, this grid here. It's about 3 millimeters on the side. So that little 3 millimeter chip requires a room which is about 10 feet by 10 feet by 10 feet to operate properly. But that's what the quantum chip is. And it consists of an 8 by 8 array of a repeating unit cell structure. The device is made out of niobium, and we have 6 layers in the current chip. So if you were just to be presented with a chip, you'd only see the surface layer. So one of the keys to our success has been, as we make a chip, right next to it, we make each of the layers independently. That means if we get the wafer back and the quantum processor not working correctly, we can probe each of the individual layers of electronics to isolate where the problem is. We also have a technology on the chip for storing the problem locally at superconducting temperatures. So you pose your problem once from room temperature down to chip, and when you repose the problem, it can get loaded in very quickly because it's stored locally on chip. So the chip actually uses a combination of quantum superconducting electronics as well as classical superconducting electronics. So at its core, the qubits consist of loops of niobium with the Josephson junction, the standard flux qubits. And we have loops within loops where we can thread flux for fine-tuning the qubits. And the loops within loops serve a couple of purposes. So the first purpose is, since you have a loop of superconductor with a Josephson junction, if the current is going one way, it can generate a spin up, and if it's going the other way, it can generate a spin down. And because it's quantum mechanical, the current can flow both clockwise and anti-clockwise simultaneously, so you can get a superposition of spin up and spin down. But what we want to be able to do to make this a programmable icing system is we want to be able to apply a bias magnetic field to each of the spins individually and a coupling between the pairs of spins on the chip. So we mediate all that by loops of superconductor and Josephson junctions. Now, this is a very simplified diagram of what the qubit actually is, because one of the key things you find out very quickly when you try to make a quantum computer at scale is to make it work, you need all of your quantum bits to be identical. And it's not possible to fabricate hundreds of quantum bits so that they're truly identical. So when we make our qubits, we design them so that we can apply additional fluxes through additional loops that aren't shown here that lets us calibrate the qubits after they've been fabricated. So once we get a chip back from the foundry, when we install it at a customer site, we have to go through quite a long calibration process to get all of the qubits as close to identical as we possibly can. And then when it's in that state, we can start to program it as a quantum computer. So if you looked at the chip under a microscope, it would look like this array of a 3 millimeter by 3 millimeter array of this 8 by 8 repeating unit cell. Now, if you were to blow up one of those unit cells, the structure you would see is on the right here. Now, on the last diagram, I showed the qubits as sort of rather square-like structures, loops of superconductor. What it actually looks like on the chip is you imagine taking those squares and stretching them out, make them very elongated. This is the actual qubit structure, this elongated rectangle. And so each unit cell consists of 4 vertical qubits and 4 horizontal qubits. And where those qubits overlap, we put a coupler. So the physical pattern of qubits that you see here induces a logical graph of qubits here. So the qubits in this diagram are now represented by dots, and the couplers by edges, whereas in this diagram, the qubits are physical, elongated, or sort of bands of superconductor, and the couplers are where they cross. Now, what's interesting about this graph, the logical graph of the qubits, is that although it's quite sparse, it's non-planar. And that non-planarity is critically important from a computer science point of view, because from a computer science point of view, the problem of determining the ground state of a planar Ising model is in P. It's an easy problem. But the problem of determining the ground state of a non-planar graph is exponentially difficult in the worst case. It's NP hard. And so we use that fact that the problem the chip solves natively is NP hard in order to program it. Because computer scientists know of lots of mappings from one NP hard problem to another with just a polynomial cost. So the way you program the chip is you pick your problem that you want to solve, which is typically an NP hard or NP complete problem, and then you use one of these polynomial cost mappings to map it into the particular NP hard problem that the chip solves natively. That's essentially how you do the programming at the very lowest levels. So to a physicist, the problem that the chip is solving is to find a configuration of spins, S, that minimizes this objective function, the Ising Hamiltonian. We can program in a bias on each of the individual qubits, and we can program in a coupling on each of the pairs of qubits that are connected in the working graph of the processor. And by a simple transformation of variables, we can change from spin variables to binary variables, zeros and ones. So the spins are -1 and +1, and the binary variables are, of course, 0 and 1. But there's basically 2 sets of literature you can go looking at for ideas for how to program this. One is the physics literature of Ising spin systems, and the other is the computer science literature on what are called QUBOs, quadratic unconstrained binary optimization problems. So the working graph of the processor is this graph we call the chimera graph. You can sort of see it underneath the colored lines here. The reason we picked this graph is not that we want to solve Ising spin problems on chimera graphs. That's not very interesting. The chimera graph has a very interesting property, though, in that you can embed a complete graph within it. So that means if you make a big enough chimera graph, you are able to embed any Ising problem in that graph that you want. So that's why we picked the chimera graph. And our colleagues at NASA Ames, who have one of our processors, recently looked at some problems, which is finding ground states of fully connected spin glasses using this technique. Now, to do this embedding, how it works is you have to create an elongated qubit by ferromagnetically linking a sequence of qubits together in a chain. And then all these qubits can be made to behave as one long qubit. And so if you want to connect a qubit in the bottom left chip to a qubit in the top right of the chip, you can do so by connecting the dark blue chain to the cyan-colored chain at the top. Okay, and then to program the chip, you don't actually have to set the biases and couplings individually. You can basically use a programming interface, which currently is written in either Python, MATLAB, or C++, and you specify your biases and couplings just as a big matrix So the diagonal elements are essentially the biases, and the off-diagonal elements are the couplings on the chip. So if you can program in Python, MATLAB, or C++, you can write a program that interfaces to the D-Wave machine actually very easily. And not only that, you can run it remotely. So you can be sitting on your desktop, at your desktop in Helsinki, and you can command a quantum computation on a D-Wave machine in Vancouver. And from the very beginning, the architecture was built to support internet protocol, so it works from anywhere over the world. And we have an ongoing competition at D-Wave to see from what kind of a device we can do quantum computation from. And so far, we have it going on from planes in mid-flight to boats to you name it. So if you were to look at the chip after it's been programmed, it would look something like this. The colored lines correspond to different values of the coupling, and the colored dots correspond to different values on the bias, the individual qubits. And then when you run your computation, it means you initialize it by applying a large transverse magnetic field. That puts all the qubits in an equal weighted superposition of 0 and 1, which is the most unbiased starting point. Then you slowly turn off the transverse field as you turn on the field that impresses the problem you want to solve. And then when you do that, the qubits freeze out into 0s or 1s, and then you read off their values. That gives you one result from one quantum machine instruction. Now, as I said before, we don't actually run the computation once, slowly, and take the answer we get. We find empirically and now theoretically it's better to represent the same problem many, many times, and then take the bit string solution that most minimizes your objective function as the best relative answer found. So the D-Wave technology has been improving at quite an impressive rate over the last 10 years or so. In fact, we've been doubling the number of qubits every year, and we've been releasing a new processor about once every 4 years. So that doubling in the number of qubits is actually a faster rate of growth than Moore's law. So we've been beating Moore's law for transistors. So the current commercial product is the Vesuvius 512 system. And the one that we're about to release is what we call a Washington 1152. And the reason it's 1152 qubits is the new chip is a 12 by 12 array of an 8-qubit unit cell. So it's 12 by 12 by 8 is the number of qubits. So one thing you may read about D-Wave is people will do some experiment on the system, and they'll write a paper saying, the D-Wave machine does X. So there isn't actually any such thing as the D-Wave machine. It's constantly changing. We do about 3 or 4 complete design revisions to the chip each year. So typically, 3 months after a paper is written on one processor, the processor we now have is changed from what that was. So it's one of the keys to our success, I think, is to do really, really fast design iterations. I think anyone developing any kind of quantum computing technology should really try hard to get a very tight design, build, test cycle going, because that's the key to getting the technology to advance quickly. So here's a few applications. Conceptually, what the chip does then is it takes in an objective function defined over spin variables that you want, defined over binary variables that you want to minimize. Then it has to map that into an equivalent icing problem defined over spin variables. And then it has to embed that icing problem on the particular graph that the D-Wave chip expresses natively. And that embedding process requires creating chains of qubits so that you can essentially change the topology of the chip to your choosing. Then we quantum anneal once. That is, we put on a big transverse field, get it in the ground state, then turn off the transverse field as we turn on the field imposing the problem. And we read off the solution, convert that back to a bit string, and store the result. Then we repeat that whole cycle about 1,000 times a second. So we get 1,000 solutions to a 512 qubit problem in a second. It'll be about the same for a 1,000 qubit chip. Now, then what you do with all those solutions is really a choice. If you're trying to do optimization, you look at this pool of 1,000 candidate bit string answers you've got and the corresponding energies for each one. And in optimization, you keep the one bit string that most minimizes your energy function. That's the best relative answer found. But there's another kind of application for the chip called sampling, in which you're trying to set the biases and couplings so that you make the chip produce samples from a probability distribution of your choosing. And sampling problems have a lot of applications. Optimization problems have a lot of applications too. So they're both very, very powerful. Sampling is especially important in machine learning. It's really the key to speeding up a lot of deep learning. So one application I can talk about is one that you might not expect me to talk about. It's factoring. So we can't run Shor's algorithm on our chip. So we can't actually get the chip to do a quantum Fourier transform because we don't have the right kind of couplings and Hamiltonians. But we can factor integers. And the way we factor is surprisingly simple. So suppose you have a number you want to factor n, and you know that number is the product of two primes a and b. If you were to write those numbers out in the binary representation, you could work out a sort of long multiplication table for the numbers a and b written in binary form. So the product of the binary numbers for a and the binary numbers for b would be the binary numbers p. And what you can see very easily is there are going to be connections between what those unknown binary numbers are, p, and the particular indexed elements of the binary numbers from a and b. Yep. So the way to think about this is, imagine you wrote a multiplication circuit for binary multiplication. And on the left, you've got two 3-bit binary numbers, and on the right, you've got the 6-bit binary number, which is the product of the two input numbers. So to factor, what you're trying to do is, you know the 6 bits in the output number, and you want to find 2-bit strings for the inputs, which when you run them through that multiplication circuit will give you the bits that correspond to the bits of the number you're trying to factor. So we factor by basically writing a multiplication circuit for binary multiplication and inverting it to get inputs that give the desired output. Now, the circuit for factoring consists of 3 kinds of gates, AND gates, half adders, and full adders. And for each of these gates, we create what's called a corresponding penalty function. And this is a little tiny mathematical function defined over the inputs and the outputs of the gate, such that if that function can be minimized to a value of 0, then the values of the parameters in the function correspond to inputs and outputs that satisfy the logic of that gate. And if they cannot be minimized to a value 0, then the inputs and outputs correspond to values of the function that do not satisfy the logic of the gate. So let me give you an idea how that works. Here's the little penalty function for the AND gate. So the inputs are x1 and x2, and the output is z. So if the penalty function is x1 times x2 minus 2x1 plus x2 z plus 3z, whenever that function is 0, which corresponds to the green lines here, that corresponds to a pair of inputs and an output that satisfy the logic of the AND gate. Whenever the function cannot be minimized to a value 0, that's a combination of inputs and outputs that do not satisfy the logic of the AND gate. Yep. So now imagine constructing penalty functions for the other kinds of gates we need. We need a penalty function for the half adder. Again, when any of the green lines in this truth table correspond to inputs and outputs that satisfy the logic of a half adder, and the red ones are combinations of inputs and outputs that don't. And you can do the final thing for the full adder, you get the same behavior. So then what you do is you add up all of the penalty terms for each of the gates in your multiplication circuit. Then that is the optimization problem you pose to the D-Wave machine. You want to basically minimize the difference between the known output and the two unknown inputs, given the penalty function expressed by the sum of the terms for all of the gates in your multiplication circuit. So doing that, we find that you can factor a 2n plus 2-bit integer in 4n squared qubits using the native chimera topology for the chip. And if you wanted to, you could modify the design slightly to get that number down to 2n squared qubits. So in particular, we're able to use this technique to successfully factor a number such as 10,877 into 149 times 73. Now, by conventional standards, that's not a particularly impressive factoring feat, but it's a lot bigger than the numbers that have been factored by other kinds of quantum computers to date. So I just want to give you a flavor of that. Now, in that last example, the objective function to be minimized was known explicitly. It was the sum of the terms of all the penalty functions in the multiplier circuit. But there's another way you can use the quantum machine for a case in which you don't have an explicit closed form for the objective function. So the idea there would be, suppose you're trying to design some kind of engineering artifact, and you can represent the artifact in terms of a bit string. Then for each bit string corresponding to one of the designs, you hand it to a supercomputer, and the supercomputer takes the bit string and converts it to a model that bit string indexes for. Then you might run an expensive conventional computer simulation on that model. It could be a computational fluid dynamic model, for example. Then what you get back from the supercomputer is the bit string that the D-Wave machine provided and a corresponding score in terms of how good the model was that that bit string corresponded to. So what we do on D-Wave is then we learn from all of these pairs of bit strings and corresponding quality factors. We learn the implicit structure of the energy landscape locally. And we reprogram the D-Wave machine with the refined knowledge of the energy landscape, and we iterate that process over and over again. And in several iterations, you converge on the optimal design. And in this case, there is no closed form objective function needed. It's just a conversation between the quantum computer and a supercomputer. So why does this work? Well, if you think about doing some kind of design problem, on the vertical axis here, you've got the discrepancy between the current design you have and where you want to be, which is the 0 point on this graph, as a function of you vary some design parameter. So at any given point in the design process, you have some design here, and you have a local neighborhood you can look around. You can look at all 1-bit flips, all 2-bit flips, all 3-bit flips. But you can't look at too many of those because there's combinatorially many of them. So you've taken off in what looks like the best direction, which is sort of down here in this direction. Now, conversely, with a quantum machine, in one go, you can tunnel your way through to a better local minimum. So you can have a bigger horizon to look around, and you can take a step in possibly a different direction from what the conventional machine would do. So then in fewer big steps overall, you can be taken to a better optimum. So one example where we've done this, we worked with a cancer hospital in Canada, and they have patients who present with tumors. And the computational problem they have to solve is they have to decide from what orientations you're going to inject radiation into this patient and at what intensities, so that where all those beams intersect on the tumor, you deliver enough radiation to kill it, but you want to minimize the collateral tissue damage to the patient. You don't want to put radiation through their brain or their eyeball, for example. So in this case, the design of the radiation treatment plan is represented by a bit string, and the quality of the plan is the result of running a radiation transport model on the particular three-dimensional structure of the organs for that particular patient. So the hospital was using a taboo solver to do this minimization before, and using the D-Wave machine for this patient, they're able to minimize the treatment plan to a lower value, which means that the patient got the lethal dose on the tumor, but there was less collateral tissue damage. But more interestingly, the number of times the radiation treatment model had to be called was only 1/3 as many times. That saved HPC cycles. So it's an interesting kind of application to think about of where maybe a quantum computer and an HPC computer can be used synergistically so that the quantum computer can guide the explorations of an HPC. Okay. Anyway, those are just two examples of some of the things we've done with the machine. We've done a lot more besides. I can talk about some another time. So the two questions that come up a lot lately are, is it quantum and is it faster? So what do we know about those two questions? So the first question, is it quantum? Well, the evidence for quantumness is now pretty good. So most notably, we actually have a paper out that shows that we use the quantum chip as a kind of programmable physics lab on a chip, in which we use one of the qubits in one of the unit cells as a probe qubit to measure the energy eigenbasis and occupation numbers of a set of other qubits on the chip. So using the quantum chip as like a little programmable physics lab. And then once you know the energy eigenvalues and occupation numbers, you can work out the density matrix for the test qubits. And from the density matrix, you can work out the entanglement measures. And we used concurrence and negativity and a witness based on magnetic susceptibility. So the solid lines correspond to the theoretical predictions, and the data corresponds to what the D-Wave machine did. And what the data shows is that we have a significant amount of entanglement at the critical stages of the annealing process. So what you should realize is the way this machine actually works, it goes through a staged process of first a coherent evolution, and then the solution will freeze, and you go through an incoherent evolution. So you have both coherent tunneling and incoherent tunneling going on in this device. But it does have entanglement that we've confirmed and measured. And I think that is actually a world record for the most entanglement shown in superconducting qubits to date. So that's clearly quantum mechanical, because classical systems can't be entangled. Similarly, a group at USC and UCL looked at different models for the D-Wave device. So, for example, a group from IBM had proposed a particular classical model of the D-Wave device. And the group at USC and UCL looked at that model and others, and after several rounds of sort of ping-pong between IBM and UCL and USC, it sort of settled in version 3 of the paper that shows that there's excellent agreement between the D-Wave system and a quantum mechanical model across a wide range of effective temperatures, and there's poor agreement with the classical model, this spin model from IBM. So that paper basically concluded that this device fits a quantum mechanical model without any fine-tuning of parameters across quite a wide range of effective temperatures. And the classical model doesn't fit. In fact, none of the classical models proposed so far fit. So that's good. Then the USC team recently have been working on a new approach to quantum error correction for quantum annealing. So we have a very good theory of quantum error correction for gate model quantum computing, but we don't really have nearly as mature a theory for quantum annealing. And the reason we don't is, in part, quantum annealing itself was chosen by D-Wave because it's inherently a lot more resilient to noise natively. So a lot of the processes that afflict a gate model quantum computer cause an error are actually beneficial in our model. So if you have a relaxation process that pops you down from an excited state to the ground state, that's actually good news for us. We want to be in the ground state. Whereas in a gate model, that would correspond to a bit flip error. And then finally, recently there was a paper by Google and NASA that showed not only is the quantum tunneling going on the D-Wave device, but they were able to construct a class of problems that could prove that the tunneling is playing a functional role in the computation that the machine is performing. So it's clear that the machine is quantum mechanical in many ways at this point. So the next question then is there a quantum speedup? So the reason you might think there isn't, there's been some negative reports on this, but you have to look at these reports really carefully. And trying to do benchmarking on any kind of quantum computer is a lot more complicated than you realize, because any one test will only look at one aspect of the problem or another. Someone in D-Wave described this to me as trying to describe what an elephant looks like by having a group of people sort of hold parts of the elephant and describe what they're feeling to each other. It is a little bit like that. So the first thing you might have heard of is the D-Wave machine is indeed a non-universal machine, and it has a Hamiltonian which is called stochastic. It just means that the off-diagonal elements are real and non-positive. And the reason it's stochastic is we don't have an XX coupling or an XZ coupling in our Hamiltonian. We know how to make one, but the current chip doesn't have one. So there have been some theory proofs from computer scientists that show if you have a system described by a stochastic Hamiltonian and its couplings are purely ferromagnetic, then you can simulate that system efficiently classically. There's another proof in the classical computer science literature that if you have a Hamiltonian that's frustration-free and stochastic, you can simulate it efficiently classically. But the problem is the computations that arise as hard examples in real-world applications are never only ferromagnetic couplings and they're never frustration-free. In fact, there's usually rife with frustration. So those particular theorems from classical computer science don't really shed any light on how this machine behaves on the hard problems. Secondly, when we did our benchmarking with Google, Google asked us to benchmark against Cplex, which is a sort of flagship IBM optimization product. And we found that the D-Wave machine was about 10,000 times faster than Cplex on some class of problems. So in response to this, IBM pointed out that there's actually a polynomial time approximation scheme for solving Ising spin problems on this chimera graph on the chip. Well, that's true. There's also a polynomial time approximation scheme for a traveling salesman problem, but everyone still regards that as a hard problem. So the reason this doesn't really make any difference is that although this PTAS scales linearly in n, the number of qubits, the prefactor scales exponentially in the inverse precision. So if you wanted to get within 1% of optimality, this prefactor constant is about 2 to the 3200, or 10 to the 963. Now, 10 to the 963 might be just another constant to a complexity theorist, but to anyone making practical hardware, that the number of particles in the universe is like 2 to the 300. So 10 to the 963 is essentially an impracticably large number. It doesn't really surprise me, because like I said, there are PTASs for other problems like Euclidean traveling salesman, which are still regarded as hard problems. Now finally, you probably heard some work from the group at ETH showing that the D-Wave machine scaled about the same as a classical solver on these random chimera problems. But there's another paper that came out from Katzgraber that explained why this was the case. It turns out that these random +1, -1 problems on the chimera graph are anomalously easy. So basically, there's no opportunity for quantum tunneling to kick in and show an advantage because the energy landscape just is too simple to navigate classically. What Google showed is if you change the problem and you make the energy landscape be characterized by having a lot of hills and valleys, very deep valleys and narrow, tall hills, then on those kinds of energy landscapes, the D-Wave hardware scales a lot more flat than the classical thermal annealing. So there's clearly, the hardware is doing something very different from thermal annealing, as this data shows. But you do have to pick your problem ensemble class carefully to get any useful information about what the scaling is. So what we're doing now is we're looking for harder problem sets for benchmarking. One of the things we looked at is there's a phenomenon in computer science known as a computational phase transition, where you pick your favorite NP hard problem, could be say 3-sat or graph coloring or whatever you want, and you look at the cost of running a classical algorithm to solve that problem as a function of a structural parameter of the problem. So for 3-sat, it's the cost of running a good algorithm like Davis-Putnam or something. And on the horizontal axis, the ratio of the number of clauses to the number of variables in your 3-sat problem. And what you find at the critical ratio, where the problem goes from being almost surely at the critical ratio when the problem goes from being almost surely satisfiable to unsatisfiable, the hardest instances tend to cluster. And that kind of computational phase transition phenomenon is very pervasive in computer science. So we looked at other problems that have those kinds of computational phase transitions. In particular, there's a variant of 3-sat called not all equal 3-sat, and another one called 2 in 4-sat. And for those variants, which map better to the hardware, we can look at the performance of the D-Wave machine versus some of the specialized solvers that were made to compete with the D-Wave machine. So one of those solvers is simulated annealing. So on the vertical axis here, you see the time it takes to solve a 3-sat, not all equal 3-sat problem on the D-Wave machine versus the time it takes using thermal annealing. And the data points fall under the line, which means that the D-Wave machine is solving them faster than simulated annealing. Similarly, for 2 in 4 sat problems. The vertical axis is the D-Wave machine running time. The horizontal axis is the classical chip running time. And again, the D-Wave machine is solving these problems in fewer steps than the classical machine. So it's clearly performance separations between what the D-Wave machine does and what good classical solvers can do on hard problems. But you've got to make sure you're working on problems that are worthy of attempting to solve them quantum mechanically. The other thing we're doing is looking at performance metrics that are less sensitive to one of the problems we have with the chip. And one of the problems with the current chip is that when you specify the H's and J's as your problem, then the values that are expressed on the chip are not always, in fact, they're never identical to the values requested because of noise. And on the Vesuvius chip, the noise level was about 5% in total, crudely, which is quite a significant error. So what we think the Vesuvius chip was really doing was giving a very good answer to the wrong problem in some cases, okay? So we believe this because one of the benchmarks we did with Google, which didn't get as much attention as some of the other ones, was this one. We looked at the approach to optimality as a function of the running time of the algorithm. So the colored curves are, this is the IBM Cplex solver, which is the flagship optimization engine. The yellow curve is AK-Maxat, which won international competition for solving weighted max 2-set problems, which is essentially what our chip solves too. And the green curve is Taboo. The vertical axis is how far away you are from optimality as a function of the running time of the algorithm. So you see that the classical solvers typically start off with a sort of poor solution, and then they get better over time and approach optimality asymptotically. The D-Wave machine goes along this line. First of all, nothing is happening here, because this is how long it takes us to pose the problem to the machine. So the machine doesn't even get the problem until this point here. Then the first time you turn it on and get an answer, you get a really good answer. That's always the case. We always get really, really good answers. May not be the global optimum, but it's always really good. And that's because what the chip is doing is drawing samples from a Boltzmann distribution at the operating temperature of the fridge, which is 20 millikelvin. And Boltzmann distributions at that temperature are strongly peaked towards optimality. So the message here is that the chip is very, very good at getting close to optimal very quickly. So the idea is, what if we can pick a metric that looks at that explicitly? So here you have some graphs of increasing precision in the problems, and the scaling of the algorithms when you're looking for global optimality versus looking for optimality within epsilon or some distance of global optimality. And the key message here is that scaling curves that might look unfavorable for the D-Wave machine when you're looking for global optimality, such as this curve here, this top blue curve on the left, that scaling disadvantage becomes a big advantage when you look for optimality to within epsilon. So some of our new benchmarking studies we're going to do this year is going to focus more on problems for which we don't necessarily need global optimality, but we need optimality to within some neighborhood of global optimality. Okay, so I'm going to end with a quick preview of our new upcoming product. This is the first 1,000-qubit processor. So our current processor is the Vesuvius 512-qubit processor. As we were making the 1,000-qubit processor, we made a Vesuvius V7, which is one generation later than the V6 our customers have. And we ran the same benchmarks on V6 and V7. And V7 basically had some design improvements for the component qubits. And what you can see here is that on the same benchmarks, the gradient of those scaling curves has gone down from V6 to V7. That's very interesting, because what it tells us is there was nothing fundamental about quantum annealing in those original scaling curves. Because if there was, or as you go from one generation to the next, all you could possibly do would be a parallel translation of the scaling curves, but you shouldn't be able to change the gradient. If you can change the gradient, it means you've not yet hit a fundamental limit on quantum annealing. So that was interesting. And then the 1,000-qubit chip is a bigger version of the V7. So here are the ways things have changed. Of course, the most important characteristic, the number of qubits has gone from 512 to about 1,100. The programming time has gone down because we have parallel lines for programming now, and the operating temperature of the fridge is going to be colder, so that should push us more towards global optimality. So here's a wafer showing actually 3 generations of D-Wave processor. The small chip is the 512 qubit, the mid-sized chip is the new processor, and we have the next processor in development, the 2000 qubit chip, which will be coming out sometime next year, we think. This is the 1000 qubit processor, actually just before it went in the fridge. So far the performance has been very good, and we're going to be rolling out a lot of new performance results and kinds of benchmarks later in the year. So what can CQE learn from D-Wave? So one of the things that I certainly have come to appreciate is when I talk to reporters about quantum computing and D-Wave, many reporters come to me with a fairly adversarial attitude. They would like to create drama of a battle between quantum computing and classical computing. That's not reality. I've come to appreciate that what we're really offering is not the choice between quantum versus everything classical. It's really quantum plus everything classical versus everything classical alone. That's the real choice we're offering people, you are offering people when you're making quantum computers too. As a field, that's the choice we're really offering. So I think that's really an important lesson to learn, because there's a tremendous lot we can learn and use from classical computer science, and it doesn't make any sense to try and throw it all out. We should use classical techniques where they work best, and we should use quantum techniques where they work best. Second point is, it's not all about the physics. I think everyone in this room is probably a physicist, but if you're trying to make a quantum engineering movement and get quantum engineering into widespread public use, you've got to think about the computer science too. Now, what's interesting here is there's an opportunity, I think, to create a quantum software industry. So take early stage quantum computers and create economic activity around writing software for those machines. I mean, the potential exists for the quantum Microsoft to be created right now. And what's very interesting to investors is that the leverage on quantum software companies is dramatically more favorable typically than hardware companies, because it's much easier to write software than create hardware. And already there are several software companies have started to write software for the D-Wave machine. So the 1QBit and QET branch are sort of writing in financial services. There's a couple of others that are also working in different areas too. So there's at least 4 I know of right now. Actually 5, there's 5 I know of right now. Okay, so thank you. I just wanted to thank you very much for the invitation to come and talk to you. It's a great, exciting time for quantum engineering. I think the experiences D-Wave went through have some useful lessons for us all. I think we can really all participate in the launch of this new industry. So thank you.
All right, thank you very much, Colin. Comments, questions here?
So thanks for the nice talk. You said that you make several iterations of one processor. So you're developing it all the time. How many customers do you have? Do you sell all these iterations, or is it just internal development?
During development, they're all internal. So okay. If you come to D-Wave, we have a lot of dilution refrigerators now, and they're all running on different processes at different stages through the cycle. And some processes are used to perfect the calibration code. Some of them are used for testing different kinds of benchmarks. Some of them are used for testing components. So, but design, build, and test quickly is very important.
So how many have you sold, I guess, is the real question.
In the public domain, we've sold 2, though I think there's good news coming later this year.
Okay, thanks.
All right, there was another question, perhaps Mikko there.
why does the company care if it is quantum or classical? Because what is important is if this annealing by tunneling makes things faster. I would think that that would be a...
Well, it depends on your energy landscape. So if you have an energy landscape characterized by rather shallow, rather broad hills, such a landscape is probably more efficiently traversed by thermal effects than quantum tunneling effects. If you have a landscape that's characterized by very narrow, very tall barriers, that's probably more...
Yeah, I understand this, but I mean, I think you go beyond that when you start to talk about entanglement and whatever. So just mere tunneling helps, I'm sure.
Oh, does mere tunneling help? The regime in which the entanglement is maximum is in the coherent tunneling regime. So in that regime, it's a fully quantum mechanical effect that's at work. Yeah, but there's both coherent tunneling and incoherent tunneling during the annealing process. Once you finish the coherent tunneling phase, where the entanglement is sort of maximized, you've freed out the solution. There's no entanglement then, because it's essentially a classical state, and you go through an incoherent tunneling regime. So in this device, it's a lot more complicated than a sort of theoretical model of an ideal gate model machine. You have a coherent phase and you have an incoherent phase, and they're both important. They both have a role to play.
All right, last question from Mikko.
Yes, so the PRX paper you talked about from last year, I believe you were studying there bipartite entanglement, right?
Yeah, so it was bipartite on a scale of 8 qubits was the biggest one. So all bipartite partitions of 8 qubits, yeah. So we could redo that experiment with 3 partitions, 4 partitions. It might be something we did this year. I'm not sure whether that's risen to the level of a high priority for us or not. But yeah, that was bipartite.
So, and 8 qubits, were they kind of, how far away were they in the chain? Was it a chain of 8 or?
In the paper, they were all in 1 unit cell. In the lab, we did 1 unit cell and the nearest neighbor unit cell.
Okay.
Yeah. Again, that's one of the things that I've asked for, is to redo the experiment with the qubits over a bigger range. Yeah. Yeah.
Okay, let's take the last question. Good throw.
I hate this thing. So of course, the statement you made about classical methods, not looking only at the local environment, is not true. Okay, but my question is actually, why did you not consider the traveling salesman? I missed that point. You said something about that, because that would be more representative of complicated optimization problems. Or did you consider that?
Yeah, so different problems map with different degrees of ease to current architecture. So traveling salesman is not, I would say, the easiest of the NP-hard problems to map the hardware.
Why is that? Yeah.
Yeah, so, and the reason is primarily that at the moment, the biggest complete graph you can express in the hardware is about the square root of the number of qubits, right? And so we have to go to a much bigger graph to be able to express big complete graphs.
That's what I figured,
yeah. Yeah, so, but we're also changing the, not next generation, but the one after, we're changing the architecture way that it'll make it work. The other thing, I don't have time now, but if you come up later, we have a way of programming in different topologies as a starting point for the problem using the chimera graph. So you can actually weight things so that those different topologies work better than if you program them yourself from a chimera graph. Thank you.
Sure, okay.
You made a very interesting statement about quantum Microsoft in the end. In the classical computing world, there is this everlasting discussion between software and hardware contributing to performance. So do you have any ideas or any views on how much can we contribute to the efficiency to...
Oh, yeah. Well, I can tell you internally, we have added new features to our software kit that we'll be rolling out later in the year that have a very beneficial role. So that there's improvements you can make to calibration, there's improvements you can make to post-processing, so you can take the output from the quantum computer as a starting point for something else. So the hybridizing of quantum and classical methods gives you a much more powerful system overall than relying on one or the other. Yeah.
All right, so let's thank Colin again.